We're now going to have a lightning round of 1-minute summaries of the talks for today. And holy cow. Okay, take it away, Leo.
Hi, have you ever tried proving a false theorem in calc? Turns out it's not that easy. Wouldn't it be better if you could somehow run a tactic and know before spending all the time and effort that your development has a bug? Well, with QuickCheck you can, and now it's actually easy. In our paper, Generating Good Generators for Inductive Relations, we automatically construct random data generators for data satisfying complex invariants in inductive form in order to test such theorems. If you'd like to know more, see our talk.
Great. Our next speaker is Philip Niksich.
All right. Hello. So if you feel you need a break from calc, proving things in program logics, and so on, I have for you something completely different. So to pique your interest, here's a puzzle. In a dojo in Kaiserslautern, there are N ninjas and they are in training. So they train in rounds, and in each round they split into 2 teams. We'll say that the training is complete if for every pair of ninjas, there's a round in which the 2 ninjas train in opposing teams. So the question is how many rounds you need to make the training complete. So what does this have to do with testing distributed systems under partition faults? Well, maybe nothing, but you'll have to come to my talk to see.
Hi, let's consider the sine function as an example. Since sine is a transcendental function, any floating point implementation cannot compute a mathematically exact result, and it must have some amount of precision loss. However, many implementations of Method-H library claim that such precision loss is actually very small, in the sense that the implementation mostly returns one of the 2 nearest floating point numbers to the exact result. And in our work, we automatically prove such correctness claims about Method-H library. And the key technical idea in our paper is to improve static floating point abstractions by solving mathematical optimization problems. And in fact, our static analysis is at least an order of magnitude more precise than the previous work. So if you're interested, please come to my talk in the morning session at Bunker Hill. Thank you.
Okay, next we have Moli Sagith.
Hi. So most of you heard about blockchain. Most of you have heard about blockchain, smart contract, and that they are broken and you can perhaps exploit vulnerabilities to get some money. So please, if you come to our talk, to Noam Winitzky talk, we can actually find a semantic criteria. If you follow it, then in fact you can show that these bugs cannot occur, and it's actually this criteria can be enforced efficiently, and it also enables modularity. So please come to the talk by Noam Winitzky.
Okay, we have Olivier Flukiger.
Good morning. So probably after last week, I don't have to convince you anymore that speculation is tricky. So I'm going to talk about correctness of speculative optimization with dynamic optimization. So we formalized speculation in the context of JIT compilers. And in this talk, I'm going to present you how to combine speculation and traditional compiler optimizations, and then be able to prove correctness of those optimizations. So if you're interested, the talk will be right after this lightning round in the other room. All right.
And Jose Fragoso Santos.
So, hello, I'm going to present Javert, a JavaScript verification toolchain based on separation logic. Javert aims the specialist developer wanting rich mechanically verified specifications of critical JavaScript code. I'm going to talk about the challenges that we faced in developing Javert. So Javert needed to tackle the entire complexity of the language without making any simplifying assumption, and Javert specifications need to be readable by JavaScript developers. So if you want to know more about this, come to the talk.
Okay, we have Phil Nguyen.
So we solved the problem of verifying dynamic contracts in higher order stateful languages. So software contracts are a powerful mechanism for enforcing program invariance using the host programming language with its full expressiveness. They're easy to use, but they, as runtime checks, they have obvious downsides that deter some programmers from using them to the full extent. Verifying them ahead of time would be useful, but challenging because they're arbitrary expressions with side effects that are not readily translatable to, say, first-order formulas for SMT solvers to discharge. We solved the problem using a simple operational approach based on symbolic execution. Our talk is the third one this morning in the water court room over there. Please come.
Next we have Nikki Vazu.
Hello. Today I'll talk about refinement reflection, a technique that allows complete verification with SMT. And what this basically means is that you can do theorem proving within a refinement type system. So we implemented refinement reflection in liquid Haskell, which means that we turned Haskell into a theorem prover. And here you can see some examples of proofs done in Haskell. So if you want to understand what these proofs are about, you should come to my talk right after lunch.
Okay, Zach Kincaid.
Is there a second slide on here? Or?
Yes.
Yeah, okay, great.
You have to look back, yeah.
Oh, yes, right. Sorry. So I'm going to talk about nonlinear invariant generation. The general approach that we're going to take is to treat a loop as a system of recurrences so that we can throw them into a computer algebra solver and get out this nice, say, quadratic description of the behavior of the loop. So there's two reasons that this doesn't actually work. The first is that loops are not systems of recurrences. They can involve control flow and non-determinism. And the second is that the output of a recurrent solver isn't really something I know how to do anything with, right? So they can involve things like algebraic numbers, and I don't want to really manipulate these. So this afternoon, I'll describe a mechanism for bridging the gap between the world of program analysis and computer algebra.
Okay, we have Gagandeep Singh.
Everyone knows that numerical program analysis is expensive. So if you still have not given up on it, I will describe a black box construction for decomposing all subpolyhedral domain analysis to improve performance. Our analysis is always sound, and in most practical cases, it has the same precision as original non-decomposed analysis. We have implemented it for polyhedra, octagon, and Jones domain. It is available publicly. And as you can see, you can get significant speed up with this. So if you want to learn about how our construction works, feel free to attend our talk at 2:30 p.m. today. Thank you.
You know, if you put one.
Suppose you are writing a web application that interacts with a database. At some point, you realize that your database schema just sucks. Now, not only do you need to change your schema, but also re-implement large chunks of application code. After spending countless hours making these changes, you wonder, did I introduce a bug? Well, worry not. Our tool, Mediator, can verify equivalence of database applications. If you want to learn how, come to my talk, Verifying Equivalence of Database-Driven Applications at 2:55 p.m. Bunker Hill. Thank you.
Albert Guthi.
Right. So I promise you this will be the best talk since POPL 1971. Okay? So this is about proving that algorithms are differentially private. People in the theory community are proposing algorithms. They claim that they don't leak your private information, and companies are actually implementing them. And sometimes these programs are wrong, sometimes these proofs are wrong. And these programs are complex, they're randomized, and the properties are complex and probabilistic. And we discover a surprising connection between probabilistic proofs that are called coupling proofs and program synthesis and verification technology. And we show how we can use it to prove probabilistic properties very efficiently. Thank you.
Michelle Pagani.
Okay, hi. So I will present you a new denotational model for probabilistic functional programming. So I will use a language like that one, PCF, with full recursion, a bunch of constant for dealing with real numbers and probabilistic distribution, discrete continuous. And in the model, we will interpret the types as cones, and the programs will be maps that are Scott continuous for recursion, miserable for sampling, and the real novelty of the model is the introduction of the notion of absolutely monotonicity, and what is this, and how it is related with the Gerard-Berry stability in standard PCF, and why it can play a role in the denotation of functional probabilistic programming. Come to my talk this afternoon.
Okay, we have Zach Kincaid, the second coming.
So I'm going to talk about strategy synthesis in linear games. So lots of problems in formal methods can be formalized as some sort of two-player game in logic. So for example, if I want to find a program that matches some input-output specification, I can pose this as a formula of the form, for all inputs there exists some output such that the spec holds. Or if I want to synthesize a reactive program that runs forever interacting with some environment, that can be posed as a problem of the form, for all events there exists some response, such that for all events there exists some response, and so on forever. So this afternoon I will describe algorithms for solving these types of games modulo the theory of linear or rational arithmetic.
Karthik Chandra.
Hi. Recently, Rostate and Nada Amin found a Scala program that compiles just fine, but when you run it, it crashes in the JVM. And this was really exciting because finding programs like this is hard. You know, we hope it would be hard. Well, in my talk, I'm going to describe a tool we built called Bonsai, which automatically finds programs like this. We call them counterexample programs because they're counterexamples to the claim of soundness. Bonsai finds bugs that other automatic tools can't find, and it lets you ask some other pretty interesting questions about type systems. If you want to learn how it works, come to the talk.
Thanks. Xinyu Wang.
So first of all, I really wish my talk is better than the talk from Oz. But anyways, if you have read any paper on program synthesis, and you must know that building an efficient synthesizer from scratch is very difficult. So that's why I have invented Blaze, which is a meta synthesizer that can be used in any domain. So even better, Blaze is very scalable and can outperform domain-specific synthesizers by leveraging program abstractions. So if you want to know more about Blaze, come to my talk, Program Synthesis Using Abstraction Refinement, at 440 Bunker Hill. Thank you.
Leo Stefanesco.
So the ST monad is a Haskell monad that provides ML-style mutable references. And what makes it special is this runST function that can run any effectful computation anywhere in the program. And the claim back in the original paper by Lunchberry and Peyton Jones is that all those effects are safely encapsulated. And so we prove those two theorems supporting this claim by building a logical relation using Iris. Thank you.
Ralph Jung.
Hi, I'm going to talk about Rust. Rust is Mozilla's new systems programming language with the slogan hacking without fear. So it's claimed to be memory safe and thread safe. Moreover, Rust has a focus on letting you build new libraries by writing unsafe code, that's where the type system is partially disabled, but then you're able to safely wrap this unsafe code in a typed interface so that well-typed clients still can't go wrong. So to prove that all these claims are actually true, we built a core Rust calculus, formalized it in Coq. We have a logical relation for this calculus in Iris, and then we proved type safety and safe encapsulation of a bunch of libraries. So if you want to know why Rust will also be your next favorite programming language, come see the last talk at WaterCode. Thanks.
Okay, you can see we have a bunch of great talks today, so come back at 10:30 and see the first session.
Actually, before you dash off, a quick announcement, which is, gosh, what was it? Right. The SRC, the Student Research Competition, is going to hold their final talks concurrent with the two fantastic POPL sessions, unfortunately. But the prizes, the award winners will be announced at 1:30 in Bunker Hill. So just before the Bunker Hill session starts, we will just start 10 minutes before that to announce the SRC prize winners, okay? So lunch is great, but just, have 10 minutes less of lunch so you can come and congratulate the winners. Thank you.
And let's thank all our speakers again.